Today, we'll address hydraulics in wash. Welcome to our exciting exploration of wash in hydraulics. In this lesson, we'll unveil the fascinating world of fluids and how they behave, with a special focus on their role in water sanitation and hygiene. Our lesson today will explore several issues as follows. First, we'll crack the fundamentals of hydraulics, unraveling hidden terms and key words in this field. Then, we'll study the concept of hydraulic head and energy. Next, we'll uncover the basics of hydraulics in open channel flow, like water in channels and drainage system. After that, we'll review the basics of hydraulics in closed channel flow, like water in pipelines and networks. Then, we'll review the basics of hydraulics in pumping system. We'll delve into concept of cavitation and pump curve for better pump selection. Finally, we'll explore the fascinating world of hydraulic structure and analysis, diving in the concept of dams, irrigation canals, and appropriate methods for analysis. Throughout this incredible journey, we will witness the profound connection between fluid mechanics and wash. So let's unlock the secrets of hydraulics and build a sustainable water system where everyone has access to clean water. Fundamentals of hydraulics. Water has its own unique properties. Density tells us how much water packs in terms of weight for its size. Water density is about 1000 kg per meter cube, meaning this cube of water would weigh 1000 kg, which is like a very heavy washing machine. Viscosity describes how easily water flows. Think of honey versus water. Water viscosity is 0.001 centipoise. Surface tension creates a kind of skin on the water surface, allowing some tiny things to float. So, understanding these properties is essential for designing and maintaining wash system. We are diving deeper into the world of water properties. Kinematic viscosity is another way to understand how water flows, like how fast water molecules move around. Viscosity is 0.001 millimeter squares per second. Specific gravity compares water density to a nice round numbers, making it easy to compare with other fluid or liquids. It's unitless or dimensionless, and water-specific gravity is 1 to make it good reference point. Finally, compressibility. Tell us how much water can be squeezed under extreme pressure. It's like trying to squeeze a water balloon. It is typically 2.2 gigapascal. These laws are like the rule of the games in the world of fluids. So, Pascal law explains how pressure in a fluid acts everywhere, like squeezing a water balloon. Newton's law tells us that the force can make fluids speed up or slow down. Bernoulli equation or Bernoulli equation principles is like a magic trick. The total energy of moving waters stays the same, even if the pipe changes shape. These laws are fundamental for understanding how water behaves in wash system. So, we are continuing our journey to the fascinating world of fluids. So here are some key concepts. Ludwig layer theory. Imagine water flowing in a pipe. The water right next to the pipe wall experiences friction and moves slower than the water in the center. This slower layer of fluid is called the boundary layer, like pouring honey from a spoon to a cup. The thin layer that sticks on the spoon is the boundary layer. Navier-Stokes equations. These are like super complex instructions for fluids. Scientists use this equation to predict how fluid with frictions or viscous fluid will move in different situations. For our wash purpose, we will not dive too deep into these equations, but it is good to know they exist. Torricelli laws imagine a hole in the side of a water tank. Water will flow out with a certain speed. So Torricelli laws help us calculate the speed based on the height of the water in the tank. This is useful for understanding water pressure in wash system. Let's explore some additional concepts related to fluid motion. Leonhard Euler's in viscous motion. Imagine an ideal fluid with no friction. Euler's works help us understand how such a perfect fluid would move. While water has some frictions, understanding in viscous motions help us grasp certain fluid behaviors. Archimedes' law of buoyancy. Have you ever noticed how a ball floats in water? So Archimedes' law explains why. It tells us that an object submerged in a fluid experiences an upward force equal to the weight of the fluid displaced by the object. This is why both flows. Poiseuille's law for flow rate. Imagine water flows through a thin tube. Poiseuille's laws help us calculate the rate of flow, how much water passes at a point each second, based on the tube size and the pressure differences between the ends. This is important for designing pipes in wash system. Fluid can flow in different ways, and these are called flow regimes. The Darcy-Weisbach equations are mainly designed for closed systems, like pipeline. This equation helps us understand how friction affects flow in the pipes, like closed system. It's a bit complex, but it's like a recipe for calculating pressure drop in pipe due to friction. Manning equation is mainly for open channel, like drainage. So imagine water flows in an open channel like a ditch or drainage system. Manning equation help us calculate the flow rate in open channels considering factors like the channel shape, slope. Reynolds flow regime. This concept tells us whether a fluid flow is smooth, called laminar, or chaotic, called turbulent. It depends on a value called Reynolds number. Understanding flow regimes is important for wash system because turbulent flow can cause problems like increased pipe wear or difficulty controlling flow rate. So imagine water flows in a pipe at low speeds. The flow might be smooth and orderly like a parrot. This is a laminar flow, but at the speed increase, the flow can become chaotic or unpredictable called turbulent flow. The Reynolds number helps us predict the type flow will occur. So laminar flow generally has a Reynolds number less than 2000. Critical flow between 2000 to 4000. Turbulent flow with Reynolds number greater than 4000, called chaotic, unpredictable, or rapid flow. Flow rate simply means how much water passes through a certain area in a given amount of time. It's like measuring how many cars passes a point of a road each second. We can calculate flow rate using the equation Q equal velocity times area. We can measure flow rate with special meters or even time how long it takes to fill a container of a known size. Now we are venturing into the exciting world of hydraulics head and energy. These concepts are crucial for understanding how water behaves in wash systems. Hydraulic head represents the potential energy stored in water due to its elevation, pressure, and velocity. So, by understanding these components, we can design systems that move water effectively to where it's needed. Imagine a bucket of water held high above the ground. The water in the bucket has potential energy because of its height. Static head is like the potential energy stored in water due to its elevation above a reference point. The higher the water is, the greater static head. We can calculate static head using the equation H equals Z, where Z is the elevation of the water relative to the reference point. So choosing the right reference point is important. Imagine water flows rapidly through a pipe. The moving water has kinetic energy due to its speed. Dynamic head is like the kinetic energy stored in water because of its velocity or speed. The faster the water flows, the greater the dynamic head. So we can calculate dynamic head or H using the equation H equal V squared over 2G, where V is the water velocity and G is acceleration velocity due to gravity. Imagine squeeze a balloon full of water. The pressure inside the balloon pushes outwards. Pressure head is like the potential energy stored in water due to pressure action on it. The higher the pressure, the greater the pressure head. So we can calculate pressure head using the equation H equal P over rho G, where P is the pressure and rho is the density of water. It is a constant value, and G also is a constant value, represent acceleration rate due to gravity. In horizontal pipes, pressure head can often be negligible compared to static head and dynamic head for wash applications. Now we'll focus on how they apply to open channel flow. Open channel flow refers to the movement of water in channels with a free surface exposed to atmosphere. Unlike pipes where water is pressurized, open channels rely on gravity to move water. This type of flow is essential for many wash applications such as irrigation, canals, drainage, and waterways. So gravity-driven open channel flow is driven by gravity, unlike pressurized flow in pipes that may use pumps. Free surface. The water in an open channel has a free surface, not confined by by solid barriers, allowing for interaction with the atmosphere. No pressure head. Since there is no enclosed pressure, pressure head isn't a major factor in open channel flow. So open channel flow is all about gravity influence. Water flows downhill following the channel slope. The free surface flow air to interact with waters, which is different from pressurized flow in closed pipes. Since there is no enclosed pressure, pressure head isn't a major concern in open channel flow. Slope dependence. Slope of the channel bed significantly affect the water's velocity. Steeper slopes lead to faster due to gravity. Friction influence. The channel's roughness, like the presence of rocks or vegetations, creates friction that slows down the water flow. Hydraulic radius. This is key parameters and consider the channel's geometry and weighted perimeter. Area of the channel in contact with waters to influence flow velocity. So the velocity of water in an open channel depends on a balancing act between gravity and friction. So as I said, steeper slopes allow gravity to pull the water faster. However, roughness caused by rocks and weeds create frictions. The hydraulic radius considers the channel's shape and how much water is in contact with the bottom side, further influencing velocity. Robert Manning developed a powerful tool for open channel flow. Manning equation. This formula helps us calculate the velocity of water flow in open channel based on several factors. Manning equations derive from observation and measuring flow rates in various channels. The formula considers the Manning roughness coefficient, which depends on the channel materials. The hydraulic radius, the slope of the bed. By plugging these all values, we can estimate the water velocity in an open channel. Slope selection. The slope of the channel bed is crucial design decision. Steeper slopes allow faster, but may require like sturdier channel walls to prevent erosion. Channel shapes. Open channel can come in various shapes such as rectangular or triangular. So each shape has its own hydraulic properties and construction consideration. Material selection. The channel materials need to be chosen based on factors like durability, cost, and flow characteristic. Now we'll explore different flow regime in open channel. Unlike pipe, where flow is often uniform, open channels can experience variation in flow depth and velocity. Non-uniform flow, called severe flow. This occurs when the channel shape changes significantly over a short distance, causing inconsistent flow depth and velocity. Critical flow. This is a special condition between uniform and non-uniform flow. At critical flow, the water flow velocity reaches its maximum value for a given channel depth and slope. Uniform flow or consistent. This occurs when the channel shape and slope are consistent over a long distance, leading to constant flow depth and velocity. So imagine a straight canal with a constant slope. That's uniform flow. This type of flow is simpler to analyze and design. Now, non-uniform flow can be further categorized based on how rapidly the flow changes. It can be gradual or rapid. So gradual varied flow or steady change occur when the channel shape and slope change gradually over long distance. While rapid varied flow or any steady state, this occurs when the channel shape or slope change abruptly or suddenly over a short distance, causing a sudden and significant change in flow depth and velocity. We have explored open channel flow. Now let's shift our focus to closed channel flow. This refers to the movement of water within enclosed pipes or tubes. So the Darcy-Weisbach equation is a powerhouse tool in closed channel flow or pipeline. It helps us understand how to calculate the head loss that occurs due to friction between the water and the pipe. When I mean pipe, I mean pipe wall, the internal wall. As water flows through a pipe, friction slows it down, and this lost energy represented by head loss. The formula considers factors like the pipe length, diameter, water velocity, and friction factors that depends on the pipe's roughness and flow regime. By using Darcy-Weisbach equation, we can design piping system that minimize head loss and ensure sufficient water pressure reaches all the desired location in a wash system. Bernoulli principles is another term for closed channel flow. It tells us that in flowing fluid along a streamline, there is a trade-off between pressure, velocity, and elevation. The total mechanical energy should be constant. Imagine a pipe with a narrow section. As water flows through the narrow part, its speed increases due to the same amount of water trying to pass through the smaller area. And according to Bernoulli principles, the pressure in the section decreases. Once the water exits the narrow section and enters a wider area, the flow velocity decreases while the pressure increases back to its original value. So understanding this principle is crucial for various applications in wash system, such as design pumps and analyze flow behaviors in pipeline. Reynolds number is a dimensionless quantity in fluid mechanics that characterizes the flow regime. It is a ratio of inertial forces to viscous forces within a fluid. In simple terms, it tells us whether the flow of fluid is smooth or chaotic. Low Reynolds number indicates smooth laminar flow, while high Reynolds number represents turbulent flow or chaotic. The Reynolds number is a very important concept in fluid mechanics, and it's used in a wide range of applications, such as designing pipelines, airplanes, or ships. Louis Ferry Moody, or Moody diagram, was a brilliant engineer who made a significant contribution to the field of fluid mechanics. His diagram is a widely used tool that is essential for designing pipelines and other fluid systems. The Moody diagrams allow engineers to calculate the pressure drop in a pipe, which is critical for ensuring that the pipe can safely handle the flow of fluid. Moody diagram is a complex but essential tool for engineers who work with fluid flow. The diagram can be used to determine the friction factors in a pipe, which is used to calculate the pressure drop in the pipe. The pressure drop is important for designing pipeline and other fluid systems, as it affects the flow rate of the fluid and the amount of energy that is required to pump the fluid. Moody diagram can be difficult to use, but there are a number of resources available to help engineers understand and use the diagram. Now it's time to delve into hydraulic analysis. EPANET is a free and widely used software developed by U.S. Environmental Protection Agency, EPA. It's a powerful tool for modeling and analyzing pressurized water distribution system. EPANET capabilities include simulating water flow and pressure throughout the network, analyzing water quality within the system, and evaluating different design scenarios and operational strategies. It's an invaluable asset of water engineers and professionals. It allows us to build virtual models of water distribution networks, incorporating components like pipes, nodes, junctions, pumps, tanks, and reservoir. So we can simulate how water behaves within the model, considering factors like flow rate, pressure change, and even water quality variations. So this simulation capability allows us to analyze different design options, predict potential issues, and optimize the performance of water distribution system before physical construction takes place. So time for pressure management. Pressure management is a crucial aspect of ensuring efficient and reliable operation in a water distribution system. Maintaining optimal pressure levels throughout the network is essential for several reasons: preventing pipe rust and leaks, reducing energy consumptions, improving water quality. Water hammer is a pressure surge that occurs when the flow of water in a pipe is suddenly stopped or interrupted. This rapid change in a momentum can cause significant increase in pressure, potentially damaging pipes and valves. Common cause of water hammer: quick closure of valve, pump shutdown, system failures. So water hammer is a serious concern in water distribution system. The sudden pressure surge can cause pipes to crack, valve to crack as well, and even meters to break. The formula we see here help us calculate the pressure surge caused by water hammer. So it is necessary to understand this concept of water hammer. District metered area is defined zone within water distribution system called DMA, are created by strategically placing isolated valve to divide the network into smaller manageable sections. The benefit of using DMA: leak detection and isolation, pressure management, reduce water loss. So this district metered area are a powerful tool for managing water distribution system by dividing the network into smaller zones. So DMA enable us to pinpoint leaks more efficiently, optimize pressure control, and ultimately reduce water loss. Flow meters installed within DMAs provide valuable data on water consumption pattern, allowing for better water management and water resource and demand assessment. Isolation valves within DMS allow for isolating leaks and repairs without disrupting the entire system. This slide showcases a sample layout of a DMA. So as you can see here, the DMA is defined area within a single entry point of water and a single exit point. So flow meters at point can track the volume of water entering and leaving the system. Let's delve into hydraulic principles apply significantly to pumping system. There are several key hydraulic terms that are crucial for understanding pumping system. First, cavitation. This is a phenomenon that occurs when the pressure in the liquid entering a pump falls below its vapor pressure. This can cause bubbles to form in the liquid, which can collapse violently when they reach areas of higher pressure. Cavitation can damage pump components, reduce efficiency, and create noise and vibration. Cavitation might lead to pump efficiency issues, which is a measure of how much hydraulic power output from pump is achieved compared to mechanical power input. Net positive suction head. This is critical parameter that specifies the minimum pressure head required at the pump inlet to avoid cavitation. There is two components, net positive suction head required and available. The available is the pressure head available at the pump inlet, while the required is the minimum pressures as specified by the manufacturer to prevent cavitation. System curve or pump curve. This is a graph represents relationship between flow rate and pressure drop or head in piping system. The system curve essentially shows how much pressure is required to overcome resistance in the system at different flow rate. It helps in pump selection. For choosing the right pump for a specific application required careful consideration of factors like flow rate requirement, pressure head, net positive suction head, and system characteristic. The system curve is a fundamental concept in pump selection. It represents the relationship between flow rate and pressure or head. In a specific piping system, the system curve essentially tells us how much pressure is required to move a certain amount of fluid through the pipe at different flow rates. This curve is specific to the piping system configuration and resistance. This slide shows a typical system curve. As you can see, the curve slopes downward from left to right. This indicates that the flow increase, the head pressure required to overcome resistance in the system decrease. This is because higher flow rate lead to higher velocity, and overcoming velocity head becomes more significant factors compared to friction losses at lower flow rates. So it is necessary to understand this kind of curve for proper pump selection. Cavitation is a determined phenomenon that can occur in pumps when the pressure of the liquid at the pump inlet falls below its vapor pressure. This pressure drop can cause the liquid to vaporize, forming small cavities or bubbles within the liquid. As these bubbles travel throughout the pump to areas of higher pressure, they collapse violently. This rapid collapse can damage pump components like impellers and create noise and vibration, significantly reduce pump efficiency. So, pressure affects the boiling and freezing points of water. The standard boiling point of water is 100 degrees Celsius at atmospheric pressure or 1 bar. As pressure decreases, the boiling point also decreases. Water boils at a lower temperature. Conversely, as pressure increases, the boiling point increases. Water requires a higher temperature to boil. Similar principles apply to freezing point of water. So this slide illustrates how pressure can influence the phase of water, especially the boiling and freezing points. We typically associate the boiling point of water with 100 degrees Celsius, but this is only true at standard atmosphere pressure, 1 bar. When pressure decreases, the vapor pressure of the liquid increases. This means that water molecules are more likely to escape the liquid and form vapor at lower pressure. As a result, the boiling point of water decreases as pressure drops. Conversely, higher pressure. Now, net positive suction head is a critical parameter in pump selection and operation. It essentially refers to the minimum pressure required at the pump inlet to prevent cavitation from occurring. So there are two key aspects. The required, which is the value specifying by the pump manufacturer and represent the minimum pressure head required at the pump inlet to avoid cavitation at a specific flow rate. While the net positive suction head available is the value calculated based on the system condition and represent the pressure head actually available at the pump inlet. So to ensure cavitation-free operation, the available must always be greater than the required. So the formula provides here help us calculate the net positive section head available by considering atmospheric pressure, static head, and friction losses. We have now covered important concepts in hydraulics applied to pumping system. So now let's shift to focus on civil engineering structures that control and manage water flows. There is a widely variety of hydraulic structures, each with a specific purpose. Dams are massive structures that create reservoirs for storing waters. Canals are essential man-made waterways used to transport water for long distance, often for irrigation. Irrigation channels further distribute water from canals to individual farms. Crossing bridges are essential for ensuring transportation routes are not distracted by waterways. Culverts are smaller structures that allow water to pass under a road or other barriers. So all these structures all play a crucial role to managing water resource for various applications. Type of materials used for the construction dam depend on several factors like the availability of materials itself, design requirement, and cost consideration. So here there is embankment dam or all dams that made from soils, rock dams made from rocks, concrete dams made from concrete materials. Concrete dams are robust and versatile type, but there's several types of concrete dams: arch dam, buttress dam, gravity dam. Arch dam that design features as curved upstream face that transfer water pressure to the abutment. The curved shape allows the dam to withstand significant water loads using relatively smaller amount of materials compared to other dam design. Buttress design consists of thin water retaining walls supported by vertical buttress on the downstream side. These act like supporting pillars, so this can support the water pressure on the walls. Gravity dam, as the name suggests, gravity dams rely on their own weight to resist the horizontal thrust of the water. These dams are massive concrete structures designed to be stable under water pressure by their sheer weight. Dams serve multiple purposes beyond simply storing water. So it can generate electricity, and it has gates that control the water for irrigation, and spillways which can improve flooding events. Spillways are essential safety features of dams designed to safely discharge excess water that the reservoir cannot contain. They prevent the water level from rising above the dam's capacity, which could lead to catastrophic dam failure. So there are two types of spillways: principal spillways, auxiliary spillways. Principal spillways, main drainage systems of the dam designed to handle anticipated flood events, typically operate during periods of high inflow or heavy rain. Auxiliary spillway act as a secondary overflow channel used in extreme emergency situation when the principal spillway cannot handle the excess water. It may only be used infrequently during exceptional large flooding. Gates are movable structures installed at various points within a dam to regulate water flow. They serve various purposes, including flood control, irrigation release, reservoir management. There are different types of gates, include sluice gates, radial gates, butterfly gates. Sluice gates is a simple and robust versatile gates that slice up and down in grooves to regulate flow. While radial is a cylindrical gate that rotates on a horizontal axis to open or close the passage. Butterfly is a hinged gate that opens and closes like a butterfly valve to control flow. Hydroelectricity power plants harness the energy of moving water to generate electricity. Here's a breakdown of the key components involved in this process: dams and reservoir, intake gate, penstock, transformer, transmission line, generator. Also, turbine. The diagram illustrates the cycle of hydroelectric generation from dam turbine to electrical transformation. So now we'll address the hydraulic structure, focusing on canal system, which is useful for irrigation. Canals are artificial channels constructed to convey water from one location to another. They play a vital role in water resource management, particularly for irrigation purpose. A canal network typically consists of a main canal and divert water from source like river or reservoir. The main canal then branches into smaller channels called branch canals. Branch canal further subdivide into even smaller channels known as distributaries, which deliver water directly to agricultural field. The design of a canal system considers factors like topography of the land, flow rate requirement, and the need to minimize water loss during transport. So this image depicts a canal irrigation system with various canal types labeled. As you can see, the main canal acts as a primary source of water, feeding branch canals and distribute water to wider region. Branch canal then subdivide into distributaries that deliver water to even small areas. Finally, we have minors, being the smallest canals, carry water directly to the field for irrigation purpose. Hydraulic structure known as crossing plays as a crucial role in challenging water flows across obstacles like river, roads, or railways. This structure ensures uninterrupted water conveying within canal network while maintaining the integrity of the intersection road or waterways. We'll explore some common types of crossing. There are several types of hydraulic crossing, including weir, bridge, and culvert. The selection of the appropriate crossing types depend on various factors such as the size of the canal, the characteristic of the obstruction being crossed, and the design of the flow rate. Weir are a wall-like structure built partially across a river or canal to raise the water level upstream. Weirs are primarily used for flow control and diversion purpose. Bridge, a passage structure that allow vehicle or pedestrian to cross over a canal or other waterways. Bridges need to be designed to withstand the hydraulic loads imposed by the flowing water. Culvert is a short enclosed structure that allow water to flow underneath a road, railway, or embankment. So culverts are typically used for smaller streams or drainage applications. Thanks for watching my video for today, and I hope you learned something valuable. See you next time.